This meeting is being transcribed and summarized.
All right, let's get started. Good evening, everyone. So, we're going to continue our progress toward quantitative approach, right? We learned a lot about concepts. It is time that we implement some sort of approach that actually quantitative. And that's what we're going to be doing today. In fact, you see the first slide on the screen is something you've seen before. Why? Because I want to recap basically our conclusion there, right? So what we ended the previous session with was to estimate portfolio statistics, right? So first statistic, of course, is going to be the expected return, and basically the way you Excel is, you know you're gonna have to multiply two matrices, so matrix multiplication, right? And we know that the first matrix has to be transposed, so we're gonna transpose it, right? And that first matrix is actually the weight vector, and then the second matrix is the return vector. So we call it vector because it's just a column, right? So that's one thing we concluded. Then we went ahead and yeah.
Recording, right?
Yeah, that's the loud announcement you heard a few minutes ago. Thank you for reminding me. And then the next thing is components, or making sure we're gonna be able to estimate the next important statistic for the portfolio, which is the standalone risk, right, which is measured by standard deviation. And so you can do that by first estimating the covariance matrix, right? So basically, the covariance matrix, once again, is a table that collects all of the variances and covariances, where all of the variances are on the diagonal, and off diagonals you have all of the covariances between all pairs, right, of the portfolio components. And so, how do you estimate this matrix instead of, let's say, when we were talking about, I think, 100 stocks, right? And the idea is that this covariance matrix actually includes like 5,050 distinct or different terms to be calculated. So you do not want to do that by hand. You do not want to enter formulas in 5,050 cells of Excel. So that's why you want this matrix to be automatically calculated. So how do we do that? Well, it turns out that if we collect all of the columns of deviations from the mean inside a matrix called D, and we'll see an example, right? We've already seen an example, but we never called it D. When we saw the example of a column of deviation from the mean from IBM, and then the next column was deviation from the mean for AT&T. So these two columns together, let's just call it D. And again, we will apply all of this using actual numbers, but I want to make sure you see that there is a concept that does not depend on the number of stocks in the portfolio, right? Whether there's 1 million or 10 stocks, it's always the same formula. So the idea again is, you know that there's a matrix multiplication, and the first matrix is going to be transposed. Sounds very familiar. The only difference is the matrices that we're playing with. This one has to be divided by 1 over the number of observations minus 1. So, when you want to estimate or compute this particular formula on Excel, there's a multiplication, so let's do that, right? And then, the first matrix has to be transposed, so we can do that. So transpose D, right? And then the second matrix is D itself, right? So that's the matrix multiplication. And then what we do is we multiply this whole thing, or divide this whole thing by n minus 1, right? So I'm not telling you, hopefully, anything new here. It's something we talked about last time. I just want to make sure we refresh our memory, because we're going to use these formulas. So this is how you would, this formula, entering this formula, of course, is much better than entering 5,050 formulas in as many cells, right? But then once you have the covariance matrix, look at this beauty. This is the variance of the portfolio. Very short expression. Oh, and okay, so you guys have seen me so far write down Excel formulas, right? I wrote one here, I wrote one here, and I think everyone understood it. And so now I'm gonna test that hypothesis and ask you guys. So now you help me. What is the Excel formula for this? How do I write it? So first of all, there's no way around it. Clearly we multiply matrices, right? We treat it like two multiplication. So let's multiply. Right? So we know we're gonna multiply. So this is gonna be the final multiplication, right? So we first have to multiply these two, and then we're gonna multiply the product, the result, with that, right? And again, W is the vector of weights, and V is the covariance matrix, right? So let's compute this. So this is the multiplication of what? Of the transposed weight right? And you multiply the transposed weight with the covariance matrix, right? So transposed weight, and now we're gonna multiply this product with the vector of weight, right? Any questions about this, right? So that this is what it would look like if you had to write down this particular portfolio formula, right? I'm gonna stop here and then see first of all. Keep annotation to see if there's any questions so far. Right? No questions. We're all clear. Okay. So what I'm going to ask you to do is open your work from last week. So it should look something like that. And if you don't have it, I don't know, you lost it or something. This is on ASCII-CT, right? And it's called Morningstar Direct Returns with Word, right? No, I think with half the word. Mine is with the word, but yours is with half the word because basically this is done. We've done this last time, and we want to move forward. So when you guys are ready and you have this in front of you, or something like this because you did it yourself last week, raise your hand and then you're going to proceed, okay? But it's important we all have that. Because again, what we're going to be doing in this session is practice estimating these statistics, right? Now, some of you will be wondering, isn't it possible to, let's say, write code to do all of this? And the answer is absolutely, of course it is possible. However, writing code to do this, if you have no idea how to do it manually, does not make any sense whatsoever, right? It's like using a calculator but never actually never having learned how to add or multiply. So it's the same story here, right? Also, writing code is not for everyone. Some of you know that, some of you don't, right? But, so let's first do this the way it can be done without having to write any sort of code. And then, you know, if there's a need to write code, we'll do that as well. By the way, so as you guys are getting ready for this, just a quick question about writing code actually. So raise your hand if you have some knowledge of, let's say, Python. Yeah. By the time you graduate, you have to have great knowledge of Python because that's not going to work otherwise, right? The earlier you pick up Python, the better, right? Maybe we're going to do that sometime in this class, but it has become, especially because of AI, and I know some of you might, because you don't know Python, you have no idea why I'm talking about Python and AI. But actually because of the popularity of AI, particularly generative AI, right? Because of it, Python has become even more popular in finance. Now, why? Because Python has tons of AI libraries, right? Like libraries that will help you create neural networks or literally help you, come up with your own large language model, things like that. So it's already there, and that's why it's so popular. And so you need, at some point in time on your resume, to say you're fluent with Python, right? All right, I gave you guys as much time as I could. Let's see those hands if you have this in front of you, because we need it. Right? All of these results will be components to what we're going to be doing next. All right, so it looks like we have it, we all have it. So here's what you're going to do next. So, hold on, let me make this a little bit bigger. You can see that ultimately the final products we want is what I just talked to you about. Portfolio expected return and portfolio variance, right? And here I chose some random weights for the portfolio: 30% investment in IBM, 70% in AT&T, right? So the first thing for you to do is to prepare the inputs, put it on this sheet, right? So just click on the plus sign and start a new sheet. And and then when you're ready, first thing is let's have the vector we called, or I called W, right? The vector of weights, right? And you see the formula there, right? So all I did was, let me see if I can show this. Yeah, okay. Right? What did I do? On the previous sheet we had the average returns, right? But it was a row, and I don't want that. I want a column, just to localize irregular the way people do it, which is a vector, right? So it's a column. So let's write this down, this formula. Equal transpose, and then you select that row, this row. Oh, okay. Cancel, because I don't want to change anything. This row right here. Do we all see that? That's the row of expected returns for the two stocks. So the formula, once again, is equal transpose, and then select that row, and then close parentheses. Press enter. Now, these formulas that we're using are so-called matrix formulas, right? I don't know why I say so-called. They are matrix formulas, right? Now, there is a distinction for those of you who use older versions of Excel. Before you enter the formula, you have to select the whole matrix. Like in this case, it would be the two cells, C4 and C5. And then you enter the formula here, once you selected the two cells, and then Control Shift Enter, right? That if you have an old Excel. If you have the newest version, you just type this like this and it will take care of itself, right? Either way. And by the way, if you have the old version, you guys notice in the formula box, right? In my case, actually, I used it the old-fashioned way. And if you use the old-fashioned way, then you can have curly brackets surrounding the formulas, right? So now you guys see, and you know, the Excel I use, it's the new one, so it does accept both versions, right? All you need to do for most of you probably is just equal transpose, and then select the row of 2 expected returns for IBM and AT&T, close parenthesis, press enter. And now, by a show of hands, who has this vector of weights? Negative 0.15 and 0.97 on their screen. Okay, so let's wait some more. I want everyone to get this, right? Because this is just the starting point. Yeah, right. So here's the formula, right? So equal transpose. So you guys remember what transpose means, right? What does it mean, anyone? Yeah.
To swap like places.
Yeah, just you know, if it's a row, make it a column. If it's a column, make it a row. And if it's a matrix with multiple rows and columns, you take each one of the rows and make them a column, and vice versa.
So that's why it automatically populates the
Yes.
child below.
Yeah, exactly. So transpose, right? And you guys, because that's what we've been talking about at the end of our last session, and when I started this session, you guys know that the most popular matrix functions in finance are transpose and mod, right? Absolutely. Right. So equal transpose, open parenthesis, select the rows of expected returns, and then close parentheses. All right, so let me show these by a show of hands again. Who got there? Okay. All right. So I'm going to assume all of us got there, right? So now we have the vector of expected returns. Why do we need it? Well, you know, in the formula for, let's say, portfolio return, we need the weights, right, in the form of a vector. Right? Okay, the other thing we need is this covariance matrix, right? This one. We all see that? Right? So this is the one that says, well, if there's 2 stocks, basically we have 3 different terms to be estimated. If there's 100 stocks, we have 5,050 terms to be estimated. Here's the good news. It doesn't matter to us because it's the same formula. What is that formula? Well, here it is. So this is going to be more complicated, right? Let's make sure we're on the same page. Covariance is the one where we had this, right? covariance is the one where we actually use a matrix for deviation from the mean, D. Right? So let me show you what D is on our previous sheet, right? Here is D. Oh, sorry. These two columns. Do we understand it? That's D, because it's the deviations from the mean from stock one, from IBM, and this is from AT&T. And you have to put them together in a matrix. And that's the D matrix, right? The matrix of difference from the mean or deviation from it. So let's keep that in mind, right? It's like L2 to M something. Let's see, let's be a little bit more accurate. M61, L to M anyway. So here's the formula. Right? So you guys see it, right? L2 M61, that's the D matrix. So what's the formula? Equal multiplication of the transposed D with itself. So that's why you have L2M61 twice. And then the whole thing divided by n minus 1. And since there's 60 observations, we divide it by 59. Now this is more complicated clearly than the previous one. So take your time. It is absolutely crucial that you are able to enter this. Out of all of the matrix formulas that you need to be able to enter manually, this is the most crucial one. Why? Because again, it's the same formula, whether we're using 2 stocks like we have here, or 100 stocks, right? And it got so much data. And in our last session, I emphasized the need actually to consider correlations between components of your portfolio. So the formula is equal M mult, and then open parentheses transpose, and then close. Then open parentheses, select the 2 columns of deviations from the mean. Close parentheses, and then comma, select again the 2 columns, and then close parentheses, and then divide by 59. This is your opportunity to do this and practice this. You have to feel very comfortable doing this, right? Needless to say, you will have an assignment where you have to do this. I can check anyway if you can do it or not. So. And so, as usual, once you're done, just raise your hand, just so that I have some idea. Okay, we cannot have to wait for anyone. If you have trouble or anything, let me know. There's no shaming. This is learning. This is a learning space, right? So if you have trouble, ask me, and we'll talk. And definitely don't be shy.
Sir, can you hear me?
Yes, go ahead.
Can you go back to the other slide, please?
Yeah. This one, right?
No, to the same Excel, but the other sheet. Sorry, to the other sheet.
Not the slide. Okay, you're talking about.
I'm sorry.
No, not a problem. Oh, I always forget to do that. Yeah, this one. So the D matrix is this one. The LM columns. That's it. That's the D matrix, the matrix for deviations from the mean. And so folks, we have two stocks, so obviously, I shouldn't say that. We have two stocks, and so we do have two columns of deviation from the mean. If we had 100 stocks, we would have 100 columns here, right? So literally the formula was, for covariance, was equal M mod and then open parenthesis transpose and then select this, right? And then comma, and then select this again, because that's what the formula is, D transpose times D. And then close parenthesis, and then divide the whole thing by 59. So let me go back here. See, when you have 100 stocks and you wanna enter the formula for expected return without using matrices, expected return for the portfolio, you basically enter 100 terms, which I guess is doable. However, when you have to compute the variance, you do have to enter 5,050 terms. I don't think that's doable, physically doable. Yeah,
Can you still go over again, the formula?
yeah, the covariance part.
Yeah, the covariance.
So first of all, let's visualize it, right? Let's visualize it, because having the concept in mind always helps with these things, right? So this is the concept, right? That's the concept. The concept is you take the transposed deviation matrix multiplied by itself, right? So that's why we have this, you know, if we convert it into Excel, it's gonna be multiply the transposed D, right, with itself, right? And then we divide it by 59. Now, D is a specific, right, a specific matrix on Excel, right? And literally, it's this one. It is this one, right? It's the one that I said. That's D, literally, right? So this is why when you look at the formula here, you have equal M mod transpose and then open parenthesis D. I'm literally selecting the two columns on the previous sheet. And then comma D again, right? Because I'm multiplying those two together. So D is again the two columns in the previous sheet, and then divide by 59. Right? So the whole world of finance, as soon as you do it quantitatively, uses matrices. There's no way around it, right? So we might as well get very familiar with it, especially on Excel, right? In fact, everyone expects you to be very fluent with matrices on Excel, period, right? Now, if you new VBA, that's even better, right? Well, that's in the 5th semester, but that's be interesting. But the point is that at least be able to do it on Excel manually. That's absolutely necessary, right? Okay, so let me see those hands again. Who's done with this one, right? Just make sure you're done with it. Look, because as soon as there's a gap, you're not gonna catch up, because we're gonna use that. And then we're gonna use everything we're doing, we're gonna use. It's not like it's gonna stay unused or something, right? Okay, so that's covariance. All right, so now we're gonna be ready to estimate the statistic on this particular portfolio. This is a random portfolio. There's no particular reason why you should invest 30% in IBM and 70% in AT&T. But at the same time, it's my opportunity to make sure you understand that finding the correct numbers here is the portfolio problem, right? The idea is you already have the components. You already have made your choices in terms of stocks, bonds, derivatives, anything in between, right? And now you're trying to find the best portfolio, either for your client, for yourself, for some institution, or whatnot, right? Right now, I'm just doing it randomly because I want to illustrate the fact that we needed to estimate portfolio statistic, obviously, right? If you don't know the portfolio weight, you can't compute the statistics of that particular portfolio, right? So let's compute the expected return. You may or may not remember it. Let's take a quick look, right? The expected return looks something like this, right? Right here. So once again, you're gonna multiply two matrices, right? Transpose the weight and then multiply it by the expected return vector, right? So let's do that. Check this out. So I'm multiplying two matrices. What are they? The first matrix in the multiplication is the transposed C9, C10, which is the transposed weight vector. And the second matrix or vector, well, the second matrix in the multiplication is C4, C5, which is the vector of weight, right? So literally, this is the formula we're talking about. Transposed weight times return vector. So let's all enter it. And yes, because there's a, let me ask this because maybe it's not obvious to everyone. So if instead of this formula, this matrix formula, if I were to ask you now, pretend it's an interview, right? Like you were very successful in the first rounds, early rounds of the interview. Now it's a technical interview, a technical round, and I'm asking you, okay, I want you to enter the formula for the portfolio return without using matrices. How would you guys do that? Yeah.
C4
Yeah.
multiple with C9 and then plus the
Yeah.
C5 multiple with
Right. So absolutely, C4 times C9 plus C5 times C10. So with two stocks, it doesn't seem like we're saving a lot of effort by entering this matrix formula. But with 100 stocks, we do. Because with 100 stocks, we have 100 terms in the formula that you have to enter. Whereas if you use matrices, it's still the same short formula, right? So let's make sure we all know how to, type in the formula for a portfolio expected return. And as usual, when you're done, just raise your hand so that I have some idea that we can move on. Okay, let's wait some more.
So portfolio weight vector is just the other thing, right?
The portfolio weight vector, yeah, enter it manually because it's absolutely, that's a great question. Peter's question was, do we enter the weights manually as far as C9 and C10 are concerned? And the answer is right now, yes, we're gonna do that. All right. Yeah.
The sum product is basically column.
Yeah, so you can use some product, absolutely. Right. So what Fong is saying is that there's actually multiple ways of coming up with these results. Right? Absolutely. Right. All right, let me see those hands again. If you're done with the portfolio expected return, raise your hand. Okay. All right. So the next statistic we're gonna estimate for this portfolio, right, is the variance. And I was saying that for the variance of the portfolio, we have this nice matrix formula. Clearly, we have to multiply matrices twice, right? So you have to use m-mult twice. You have to transpose the weight once and multiply it by the covariance matrix, and then multiply that whole thing with the weight, right? So that's the concept. So let's do it together. So this is the formula, right? Clearly we need 2 m-mols, right? 2 matrix multiplication. And then the inside multiplication, which is the first one to be executed, right, would multiply the transposed weight, right, C9, C10, with the variance, the covariance matrix, F4, G5. So you have to be careful there, right? Because the weight is a column, but the covariance matrix is literally a 2 by 2 matrix, right? So select the right things. And then once you computed that multiplication, then you have the outside multiplication that comes into play, because you multiply that result with C9, C10 again, which is the weight vector for this portfolio. And just for comparison, let's make sure we're on the same page. And I'm gonna make sure you understand that basically if you have 2 stocks, right? As you guys, so please make sure you enter the formula, right? But if you have 2 stocks, right, the variance of the portfolio, if you had to write it down without using matrices, it looks something like this, right? Squared weight of the first stock times the variance of the first stock plus squared weight of the second stock times the variance of the second stock plus 2 times the cross product of the weight and then times the covariance between stock 1 and stock 2, right? So basically, for 2 stocks, you have 3 terms. Literally, you use every unique terms of the covariance matrix. Do we all see that? Right? So I think I've repeated this enough, but if you had to write this down for 100 stocks, how many terms do you have to type in?
10,000.
Right? 5,050. So you do not want to do that. So hopefully you have now you have an incentive to learn this. You're right here. Right? Much, much simpler. I probably should write it down for everyone online as well. So basically I was saying that for a portfolio of 2 stocks, we basically have 3 terms for the variance of the portfolio. It looks something like this. Variance of the portfolio is weight square root of the first stock times the variance. So that's the first term, and then weight of the second stock squared times the variance of the second stock, and then the cross product. So 2 times the cross product of weight times the covariance between 1 and 2. And so the whole point is that whenever you compute the variance of the portfolio, and you have to write it down without using matrices, you basically have to write as many terms as they are unique terms in the covariance matrix. And so I was saying, if there's like 100 stocks, then we know there's actually 5,050 unique terms, like variances and covariances that we don't count twice. And so that's why the variance computed using matrices makes a lot more sense, right? All right. So I hope they're not coming just because we're talking about variance. Okay, by a show of hands, who's done with this? Right? This is critical. Clearly, you guys see that this is the longest matrix formula, right, that we've been talking about. Any questions about all of these? Okay. All right, so now that we have this, why or how are we going to use these statistics? In particular, how are we going to use these statistics to come up with quote unquote the best portfolio, right? So the first answer to that is actually there is no one best portfolio. There's an infinity of excellent portfolios. So that's the good news. The bad news, of course, is we have to compute those. So let's talk about So before this particular framework known as mean variance optimization was created, basically people put together, people, meaning professionals, finance professionals, put portfolios together intuitively, right? Because there was no science, there was no nothing. And then the late Harry Markowitz actually came into play. He's the one who actually invented this, right? And I'll let you know what it is. But this work, and also his work on the CAPAM and a lot of other things, did get him the Nobel Prize in Economics in 1991, right? Now, so ever since, everything that's used in industry is a variation around this. But this is the foundation of everything, right? And then some people misunderstand it. I, for example, told you there is no such thing as one best portfolio. There's an infinity of very good portfolio. But people, for example, even professionals, right? Even professionals say, oh, this is the best portfolio because it's got the highest quote-unquote Sharpe ratio, which we'll learn. The highest Sharpe ratio. Well, that's actually wrong. You know, because if you, and I'm not gonna talk about that now because it's maybe too early. But let's talk about this. So what is this? So the general idea is that, like I said, you already have selected the individual components of the portfolio, right? So, you know, fund managers are typically not stock analysts, right? So they use the work of stock analysts and et cetera to make these selections. Does that make sense, right? You can't do everything yourself. I mean, you can do it for you, but not professionally. So, and let me rephrase that. You can, obviously, if you wanted to, but the problem is that there's a lot of very talented stock analysts already, so how are you gonna match that? And then you're gonna be a fund manager as well, right? So bottom line is, this is done, right? And the next step really is this, so-called asset allocation. Meaning, literally, the weights, right, within the portfolio, right? So much so that, by the way, if you actually manage a fund, then your performance, let's say you beat the S&P 500, maybe that's the objective, to beat the S&P 500. Your performance, let's say the alpha is the difference between your return and the benchmark return that you're trying to beat, right? So if you beat it, then the alpha is positive. You did not do so well, the alpha is negative, right? So the whole idea, one of the ways that you are gonna be judged is by looking at the alpha. So if it's positive, it's good news. But then, for you and for the client, both of you want to know, how did we get this alpha? Did we get it by choosing best performing stocks? That's security selection. And or did we get it by putting more weights on the stocks that overperform and less weights on the stocks that underperform? You guys understand this, right? So these are literally routine ways of judging funds, right? Now, so let's go forward then. So here's what happens. So when you look at, let's look at a picture where we're gonna look at all of the stocks in our portfolios on this picture. Now, here's a stock, right? Any dot is a stock. And the chart on the y-axis shows the expected return, and on the x-axis it shows standard deviation of the return, right? First, any questions on these axes, right? Is this clear to everyone? Right. So we want to visualize all of those stocks in our portfolio. And when I say stocks, please understand, of course, you may have bonds and everything else and derivatives, right? I'm just gonna keep saying stocks, just because it makes it easy, right? So we're gonna have all of the stocks on this picture, and they're gonna be dots. But you notice something. I'm also going to put on this picture not just the individual stocks, but all of the possible combinations. So that's a lot of dots. However, it turns out that when you actually look at all of the possible portfolios using the stocks that you guys have chosen right now on Stock Track, the picture will look like this area. All of these dots, right? And you notice that there's some outer envelope. You guys have noticed the blue envelope here, right? So it's not a random, right? It's not a random constellation of dots. It's got a shape, actually, right? And the shape literally looks like that, right? Now, this again includes all of the stocks that you've chosen and all of the portfolios that are possible to form using your stocks. You try different weights, right? And this is what you see on this particular picture, right? Now, given that all of the possibilities are over here, choosing the best portfolios may seem impossible, but actually, if you understand that this is return, so this is what we want return, right? And this is penalty, right? This is risk, right? Then it would make sense, to, if you want to choose a portfolio, a good portfolio, it would make sense to choose a target return right? And check this out. For this target return, what are the portfolios that are feasible? Everything on this line, is a portfolio that will give you that return. All of it. So there's an infinity, right, of portfolios with that target return. Do we all see that? Right? However, there's only one that's good. Which one is it? So again, the height is the reward, and the horizontal axis is the penalty, right? That's the risk, right? So out of that straight line, the straight line you see on the screen again is basically all of the portfolios that will give you that target return. Right? Which one is the best? Huh? The one that crosses the blue curve, right? So out of all of these portfolios, the best one is this one. Why? Because it's got the same return as everyone else on the line, and it's got the lowest possible risk. Right? That's the whole idea of mean variance optimization. Right? for a given target return, you can find the safest portfolio. Why go for additional volatility? We're gonna get the same expected return. Does not make any sense. Right? Any questions about this? No?
There's a question before having Marco, so they, just based on their experience, they could.
Yeah, just experience, there was no science to it. It was an art. It's still an art, but at least there's more quantitative support for the art.
So he came up with this concept,
Yes.
efficient frontier,
Yeah.
like kind of what you just said.
Yeah.
So that's a target,
Yeah.
Twitter we want, so there's the opportunity there.
Yeah, he came up with all of it, absolutely. So that's, it's one of those hard things to imagine, right? Because it never existed before. He actually created this whole thing, so, So, if we understand this, right? You choose a target return and basically find the safest portfolio to give you that target return. Using the same stocks that you already chosen, right? That's the idea, right? Now, however, one thing that you need to be careful about is this, and this will happen to you, and then you should know what to do. So here's the idea. What if the target return is right here? Because the person making the choice is not really interested in making a lot of money because they do not want to have a lot of risk. They understand that in finance you don't get anything for nothing, right? So maybe they choose a low return like this. Here's the questions for you guys. Based on everything that you agreed on, if I'm projecting this onto this, here's all of the possibilities, and this is the best. Is this correct?
That's what that shows.
Huh?
The return is nice.
So, but this is the choice, right? That the client or whoever it is that is making the choice want this return because they go for a lower risk, right? So this is the return, and my question to you guys is this the best portfolio? So you're saying no. Why?
Since it's below that dotted line, so the return is negative.
I know. So yeah. Well, let me write it this. Good catch. Let me write this like that. 0.
Okay.
So all returns are positive, right? Malcolm.
Well, I would say for an expected return,
Yeah.
that is less, you wouldn't want to take high risk. So you would want to reduce risk but increase on your returns. So that won't be the best choice to take since it has got more risk. And
So it looks like that, right? Absolutely. It looks like that's the best portfolio. But it's not.
But
Can you
in
guys?
terms of risk,
Yeah.
the risk is.
No, I know what you mean. Yeah, absolutely. Yeah, for that return. But can't you, look, so essentially what you're telling the client, for example, or maybe this is your fund, and what you're telling yourself is, okay, I want to shoot this return, and this is the amount of risk then that I should be accepting, right? So let me project this here, right? So this is the amount of risk, right? So we're ready to accept that amount of risk, correct? Go from there.
Because of with the same risk we take, we can have, with the same portfolio, we can have a higher return.
Yeah.
If we choose,
Yeah.
higher end.
So look, right, absolutely. So Cham just said, wait, we have this, okay, for this return, we're accepting this level of risk, right? And it doesn't look like there's anything wrong with it, but actually something is wrong with it. Because if you are willing to accept this level of risk, then you can actually get a higher return. Do we all understand this?
So
I know this is now very confusing, so let me at least make some attempt to do this again. So the whole idea was, if the target return was this, then we were willing to accept this level of risk. But for this level of risk, we can actually do better by getting this return. Do we get it?
So what is it called in finance if someone chooses, they're not optimal,
So-
it's a missed opportunity cost, or I don't know?
Well, it's not optimal, period. Right, it's just not optimal. So, what is the solution to this problem? You've noticed that when we start with a target return that's below the return of this particular portfolio, when we do that, we run into this problem. Have you guys noticed that? Right? Whenever we choose a target return that's below the return of this particular thing, which I have not defined yet, but we see a picture of it. Right? Whenever we choose a return that's below, then we run into that problem in the sense that the safest portfolio is not the best portfolio. Because the safest portfolio will have a particular risk, and given that you're accepting that level of risk, you can do better in terms of return. Right? Make sure you write that down, because it can happen that the target return is too low. Let me be very explicit with you actually. At some point in time, definitely not today, but at some point in time, given your current portfolios, right, I will ask you to estimate your expected return. And then find for that target return, find the best reshuffling that you can do to get the safest possible portfolio, right? For the same return that you're gonna get now, right? And this is the exception right here. If that return happens to be too low, you have to go through what I've just said. Meaning, instead of targeting a return, literally what you should do is you target this level of risk. Right. When we target return, we find the portfolio that has the smallest risk. But when we target a particular level of risk, we find the portfolio with the highest return. Does that make sense to everyone? So there's two formulation of the solution here. We're gonna try and minimize that, but it can happen that you have to flip-flop between those two things. You know, what I started with, and the standard way of doing it, is you choose a particular return that you want to target, and then find the composition that would be the safest for that return. That's the standard formulation. But it does happen that sometimes the target return is too low. Right. So that's the concept, and it's gonna become clearer in a few minutes. Matt?
Yeah, but well, is volatility the correct measure of risk? Because since the model actually treats upside volatility the same as volatility, it's the same risk.
So, there are solutions to that. That's a great remark. What Malcolm is saying is that, well, the way we computed standard deviation is that it was deviation from the mean from above and below, right? And he's saying, can't we do it by just looking at the downside part, right? So it's not really standard, but it is done, right? It's called sortie for example. Instead of Sharpe ratio, we sortie in a ratio, and blah, blah, blah. And we'll get there at some point, probably. But this is like the foundation, right? The reason why this is the foundation is the math is easier because the statistics are standard statistics. Like standard deviation is a well-known and studied for centuries, right? So we know a lot and we know how to manipulate. On the other hand, we just look at deviation from below, it's no longer standard deviation, right? You see the idea, right? And so the science around it is less developed, and this is why people don't really use that. But it is feasible.
The only issue
So-
you have with matrix algebra doing this is you can run into negative weights in your matrix.
Huh?
You can run into negative weights in your matrix the way you do it this way.
Well, so we're going to talk about all of it, all of that. Definitely, there's a lot of variations on this, right? But this is the foundational idea, right? And so, if you understand this, then you understand the following. So basically the solution is to make sure that the smallest return that we're targeting is this return. And then, why? Because then if we target every other return, the best portfolios are literally all of the portfolios on this blue curve, right? So, if you want a picture of all of the best portfolios, it's this, right? What I've just, I was gonna say circle, it doesn't really look like a circle, but, right? So that's basically a picture of all of the best portfolios. And the minimum return is this level of return. Every time someone tells you, or your portfolio has a lower expected return than this level, then you have to do what we just agreed on, which is flip the solution. Instead of targeting a return and finding the smallest standard deviation or variance, instead, you literally look at that target return, find out the standard deviation or variance, target that, and maximize the return, right? That will happen, right? But the picture I have in front of you is the picture of all the good portfolios. You notice that it starts with this, it starts with this particular portfolio. What is this portfolio? You notice it's the one with the smallest possible risk, correct? So it is known as the MVP, minimum variance portfolio. Very easy to remember. Questions about that? So that's the concept, right? All of your good portfolios, if you have to list them from lowest return to highest return, it will start with the return of the MVP. And technically speaking, it will end with the one stock with the maximum return. And so you have an infinity of choices between these two returns, right? The return of the NBP and the maximum return from one of your stock, right? And this, everything that's here is good, right? Anything else is bad. Yeah. Questions about it. And of course that, I shouldn't say that again, but that is what's known as the efficient criteria. So efficient in the sense of safest for a given return. Questions? Okay. So let's see what's coming. You know what? We're gonna continue on this, of course. And at some point, you'll use Excel to compute that, right? So let's take, it's 45, right? 7:45. So let's take 15 minutes, and let's all be back here at 8.
So you want me, that's what you want me to cover over at 60?
I don't know, just like.
can, well, so there's many ways of handling that. So number one is maybe your return is after tax and after service cost, correct? You see the idea? So it's not a raw return, it's just we're gonna do raw return, but feel free of course to include it. But you see the idea, right? You can, absolutely you can include, you can make these returns after tax and after transaction costs. Yeah, the efficient ratio will look different if you don't take into account these things versus the different ones. Now, when you do this in practice, let's say you work for a financial institution, that's not going to make a big difference. You pay peanuts for transaction costs and virtually no taxes. So you see the idea, right? It depends. If you do it for individuals, then it's a different story. They have to pay a lot of, if you can't be trade, you pay a lot of transaction costs, etc. But if it's in any financial institution, it's not going to be. Yeah. Great point. Yeah. So they're looking for students from different programs to talk to the team about ideas in terms of the future of the school, what could be done in the future. Yeah, online.
Sure. Yeah, the only thing I want to ask
Yeah. But I don't think it's gonna be after, usually, he's been doing these short meetings with like staff, faculty, etc. And now students. I think it's just trying to find inspiration.
And we'll learn another one like that or
Yeah. All of that.
yeah, I reply, but yeah.
Okay, thank you.
Thursday, tomorrow, yeah, she said it will be good. It's in person. Wednesday is sending all these emails. Maybe there is a separate one, but if you look at the Wednesday ones, the spam emails. Yeah, but
No, that's just for,
That's good.
real estate. It is three-story on YouTube. I learned a lot of people to use it, and really charging per story.
What is this group organized for? Oh, yeah. 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 Thank you very much.
All right, everyone, so let's pick up where we've left off. We've learned about the efficient frontier. I specifically mentioned a couple of details. Number one, the efficient frontier, meaning the list of good portfolios. Start with the MVP because it's the safest portfolio of all. And so whatever the return of the MVP should be the minimum return that we're targeting, right? And the way we get this efficient frontier is we target returns and find the safest portfolio, right, for that level of return. And the maximum return that you will find should be, should come from the stock that has the highest return, right? That's the only way you're gonna get that maximum return. One thing you should know, so this origin is 0, right? And is it true that, this picture will always have positive return? No, right? Sometimes they have negative returns, right? That's number one. Number two, you notice something here, right? There is no such thing on this picture as a zero risk asset, right? Another name for an asset like that is a risk-free asset. So the reason why we talk about this is because there is no such thing as a risk-free asset. Let me make sure you understand, right? Let's say you buy government bonds, right? Do you know in advance how much you're gonna get? Yeah. But do you know in advance how much purchasing power you're gonna get? In other words, how much stuff you can buy with the money you get from government bonds? Do we know this in advance? No. Let me make sure we're on the same page, right? So let's say we buy a government bond. I don't care how long it is. It's just a random choice. And let's say the interest rate on this government bond is, every year 4%. So if I invest $100,000, right, I'm gonna get $4,000 extra in the first year, right? And I know this in advance. Here's my problem. My problem is that, there's this nice car that I wanted, and it cost $100,000, and I had to choose between the nice car, very nice, it's very expensive, $100,000. This nice car and the government bond, right? And I'm a finance professor, so I just chose the bond. Here's my problem. At the end of the year, when I received the $104,000, I cannot buy the car anymore because the price of the car is $110,000. What am I talking about? Inflation risk. So there is no such thing as a risk-free asset. However, there are times when we can, because these are models, right? They're not always reality, right? So there are times, and I will talk about this, there are times when we can assume that government bonds are risk-free. What times are we talking about? Well, first of all, those times should be such that there's zero chance that the government will default, right? And that has been a possibility, right, in the recent past. So that's number one. Number two, and more importantly,
Well, short duration.
say again?
Short duration.
Yeah. But when we do this, in any case, we're assuming, because short duration means that when you renew your investment, it's no longer risk-free because you don't know the next interest rate on the next investment, etc. Right? So for this to be risk-free, it should be the longest possible, right? The longest bond possible. So I was saying that number one, there should be zero risk of the government defaulting. That's number one. More importantly, I've just illustrated inflation risk with my car story, right? Well, it better be true that if you're assuming that there's a risk-free asset, it better be true that inflation is constant. And that's not the case right now, right? So, yes, we can make an assumption of a risk-free asset under those two conditions. But by default, let's recognize reality. There is no such thing as a risk-free asset. So if there is no such thing as a risk-free asset, this is the solution. This efficient frontier. What I'm about to show you is how does this solution change if we assume there is a risk-free asset, right? Because you have to know what to do if your boss or you, or if your boss or your client forces you to make that assumption. Oh no, I think this is risk-free, right? But this is the solution, right? And this is the solution we're gonna be using. However, here's the point. Yeah.
Just one question, you mentioned when inflation is constant. So let's would assume that inflation is constant. Would you assume there is a government with a zero chance to default right now? That's a less measurable.
But this is my point exactly. Those two things have to be true at the same time. Inflation is constant, has been constant for a long time, and there's zero chance that the government will default.
You think, putting aside inflation, do you think there would be a...
Well, the thing is that, first of all, let's make sure we all are on the same page. First of all, there have been foreign governments that have defaulted on their debt, right? Including big countries, right? Like, for example, Russia at some point defaulted on their debt, right? You guys have ever heard of the story of the, what is it, long-term capital management hedge fund? No? LTCM? Oh, it was a very famous hedge fund. You know why it was famous? Because Merton Scholes of Black-Scholes fame, and a bunch of Nobel Prize winners were part of that hedge fund. And part of the models that they were using, like for example, Black-Scholes, right? Black-Scholes does assume continuous interest rates, no jumps, no sudden jumps in interest rates, right? What was the problem? Well, part of their portfolio included Russian bonds. And at some point, the Russian government decided that that particular bond issue, it's an international bond issue, we're gonna default on that one. There, so immediately interest rate jumped. Long story short, they were one of the first hedge funds to be bailed out by the government. Well, not bailed out in the sense that taxpayers paid a lot of money, but actually the government had to look for buyers of the assets of LTCM, and they went bankrupt. That's why it's serious when you make an assumption that like things like there is a risk-free asset. There is no such thing, period, right? But we can approximate reality if it makes our life easier. And it does make life easier if we assume that there is a risk-free asset, right? But again, make that assumption only if you're sure of those two things. There's zero chance that there's gonna be fight in Congress and then the government will default. That's number one, the US government. And then number two, that inflation that is not going up and down, right? And it has been constant for a while, right? So if we make that assumption, here's what happens. This is what happens. So you guys see the efficient frontier, right? The blue thing. But if we assume that there is a risk-free asset as in zero standard deviation in real terms, like you know in advance that if you invest in this government bond, you're gonna be able to buy that car that I was dreaming of, right? So that's risk-free, right? So if there is such a thing, check the picture, right? What do you guys see? What you see is now we're only interested in two portfolios. We're interested in this portfolio on the old efficient frontier, right? And we're interested, of course, in the risk-free portfolio or risk-free asset. These are the only two portfolios we're interested in. Why? Because whenever you combine these two portfolios, depending on if you invest more in the risk-free asset or this P portfolio, you're gonna move along this particular line, and you guys see that that particular line is better than the old efficient frontier, right? Why? Because for the same level of return, you always find something that's safer on this straight line. Do we all see that? Right? Like here. Right? If I target this return, I would have accepted this level of risk on the old efficient frontier. But now, I have a safer alternative. Do we all see that? Right? So, literally the straight line is better than the old efficient frontier, and the straight line is very simple. You invest in this risk-free asset, some of your money in the risk-free asset, and some of your money in this P portfolio, right? And in fact, this portfolio, because it's the only portfolio that we buy that includes risky assets. Do we all understand this idea? Right? Because this is risk-free, everything else is risky, correct? So all of the stocks that we're thinking of, they are all part of this particular portfolio. And there's only one portfolio. This is why this portfolio is known as the market portfolio. So let's recap, right? In reality, there is no risk-free asset, and we have to calculate the efficient frontier. And someone just mentioned to me, what happens if we take into account transaction cost and tax, etc.? Yeah, then all of these returns will change, right? And if you do it for individuals will have different efficient frontiers, for sure. Because they have different tax rates. They pay different transaction costs to their brokers. You guys see the idea, right? So this is reality. We have to compute the efficient frontier. However, anytime the question is what is the best portfolio? First, start with the efficient frontier. However, if we make the assumption that there is such a thing as a really risk-free asset, like there's no inflation risk whatsoever, right? You know in advance how many things you're gonna buy, when you receive your money from your risk-free investment. In that case, then you forget the efficient frontier. Just buy that risk-free asset and then put some money in the market portfolio. And the market portfolio is a portfolio that includes all risky assets. So for example, it includes all stocks, right? And then, because this is a portfolio, it should be defined not just by a list of stocks, but it should also be defined by the weights, right? So in this particular market portfolio, so let's call it, well, it's P, it's called a P, so in this market portfolio, what is the weight for IBM? So the weight for IBM, so this is the weight in the market portfolio. The weight for IBM is simply the market capitalization, in other words, total market value of all outstanding shares of IBM. Divided by total market cap of all stocks, right? So that's the weight, that's what this market portfolio is, right? So that's the picture. There's nothing to compute there. We just invest in two things: government bonds and S&P 500 ETFs. That's it, and we're done. Right. And you guys know, no one does that. But it's still a nice thought. It's something you need to know. Questions about this? So this line has a name. This new efficient frontier has a name, right? This is known as the capital market line. There's many names, but that's the traditional name. CML. Capital market line. Questions about this concept?
Sorry, which one is the- Oh, okay, this.
That line, just the line.
Same as the CAL.
Same as CAL, yeah.
Which is the capital allocation.
Capital allocation. Capital market line. It's the original name, and then now it's there's another name, capital allocation line. Questions about this? But this is neat though, you have to recognize it, right? If this were true, this would be very neat, because we don't need finance if this is true. We all should invest in government bonds and the S&P 500. That is it. Right. And like I said, there might be periods when that approximation is okay, and that does simplify a lot of things, right? But that's not what we're gonna do. We're not gonna assume this. We're gonna assume that in reality that's not an assumption. In reality, there is no such thing as a risk-free asset. Right? Questions about that? Okay. So now our objective is to do this. Given a set of choices that you've made on StockTrack, how do we find a list of the best portfolios? And of course, the list will include a good range of target returns, right? That's the idea. Okay? So that's what we're gonna learn to do now. Any questions, first of all? Just making sure. And of course, we by talking about this possibility, we made a lot of conceptual leaps, and that's why I'm taking my time just making sure you guys are okay with it. We all understand this? Yes? Okay.
Just one question.
Yeah.
To specific. You mentioned like in that time when Russia defaulted, they defaulted on just one couple of particular
Yeah.
governments.
Yeah, it's not all of it,
Okay.
just some.
And
Yeah.
unluckily they had that.
Yes,
I see.
yes, exactly.
Because I heard like actually a government cannot really go bankrupt in general.
Well, you read this a lot in textbooks. A government cannot go bankrupt, and And technically, this is true. Let me tell you how this is true, right? Let's say a particular government runs out of physical money, right? Guess who prints money? The government, right? So technically they can do that, but any government that have done anything close to that, they run into trouble. You know why? What happens when you print out money? What happens to prices? You get hyperinflation, right? So this is why, for example, in the US, right, in the past, and I don't know if that's gonna be true now, but in the past, we took great care that the Fed was independent from politicians. Because politicians want one thing, jobs, right? Stimulation, they put money in the economy so that, so money, there's a lot of money going around and all that, and because they want jobs. And the Fed, the US Fed's job, among other things, was to actually make sure that inflation is low and stable, right? And that's why the independence of the Fed was a big deal, right? And that may or may not be true now, right? But bottom line, if in fact the Fed does not stay independent, then this assumption is even more wrong than ever, right? Okay, other questions before we move on?
Just to know, actually,
Yeah, of course.
the highest inflation was actually in Hungary, my country. Like it price doubled every 15 hours.
How much?
Prices doubled every
Doubled
15 hours.
15 hours.
Yeah, actually.
Prices.
Yeah, the highest
But-
bill was 103 billion
Yeah, yeah.
over of 20.
But there were other governments like that.
Germany
you know.
before Hitler.
Huh?
Germany before Hitler.
Okay, but even more recently, well, not very recently, Argentina, for example, had always a big problem with hyperinflation, right? It's that, so that's the problem with this, right? It's a very nice picture, and it's a very nice solution because it makes it easy for everyone to participate in financial markets, right? You don't need to know anything. Just buy two things, government bonds and the S&P 500. That is it. You know, what's not to like there? But the problem is this assumption right here. So, okay. So let's then do the right thing. And now that we've had some experience in, calculating covariance matrix, portfolio return, portfolio variance, we're ready for this. So you guys are gonna find these data. So these are old data, so that you can't copy them. You're gonna find this Excel workbook. It's mean variance data. My type is with work because it's mine. I worked on it. You have to work on yours, right? So what is this? You have this sheet, right? So why don't you download it on your laptop and raise your hand once you have it, and then we'll discuss it. Yeah. Because now we're gonna use everything we've learned to compute the efficient frontier. as you do this, let me mention a couple of things. So when Markowitz derived this whole world, he had to make some assumptions. One of the critical ones is that stock returns are normally distributed, right? So, of course, that's an approximation of reality. Most stock returns are not as nice looking as a normal distribution, right? For example, if you look at small stocks, they're much riskier than a normal distribution. Right? So that's gonna explain my first step on this particular sheet. And as you download it on your laptop, this is the ultimate objective. So in terms of picture, it looks something like that, right? In terms of solution, looks something like that. Like I have a whole list of target return and standard deviation, and list of the weights for the individual stocks, right? So once you have this on your laptop, raise your hand. Okay, I'm gonna wait some more because we want everyone to have it on there. So why do we do that? Let me explain what you say. So obviously, I downloaded some returns, right? And when you use StockTrack, someone mentioned correctly that it's not return, it's prices, right? And so when you download prices, please make sure that you basically compute the returns, right? So again, you know, if you have two prices, you know, price number one on day one, and then price number two on day two, then this data will allow you to compute the return on day two, right? Which is price on day two divided by price on day one minus one. So that's the transformation that you need to apply to convert a column of prices to a column of returns, right? In my case, I used Morningstar Direct, and by the way, I did put out, I don't know if anyone has noticed, I put out a deck of slides showing you how to extract data from Morningstar Direct. Not as easy as StockTrack, but here's the thing, StockTrack is easy, but Morningstar Direct is used by industry, right? StockTrack is for us, right, for learning purpose. But Morningstar Direct is literally like Bloomberg, except you can have it on your laptop. So take advantage of that while you're a student at UConn, because you do have access to it for free as a student at UConn. And then you can put that on your resume that you're familiar with Morningstar Direct. Right? Again, it's not as easy as StockTrack, that's my point, but it's worth it. Also, for example, look at this, right? I did not have to worry about converting prices into returns because they already, I downloaded returns automatically, right? So what are we saying? So I'm, you know, again, make sure you have this open on your laptop, right? What am I doing here? So one of the assumptions, like I said, is that stock returns are normally distributed, right? And that tends not to be true because basically stock returns tend to have fat tails, right? I mean, extreme, there's probabilities of extreme results, right? Like extreme losses and extreme gains, right? So one way around it to make it more normal is to use continuous compounding. So continuous compounding means literally if you take these returns, what you need to do is take the log of 1 plus the returns, right? And that would be the continuous equivalent of the original return. And when you take the log of anything, those of you who know a little bit of math, log takes care of the fat tails, right? Makes it more concentrated, right? And that's the beauty of it, right? So this is I didn't invent this. This is a routine transformation. Every time you download data, just take the log of 1 plus the return, right? To make it more normal. And as it happens, that is the continuous compounded version of the return. Questions about that?
But we don't know that only have that rolling return sheet, right? Not the other one.
So this,
No, I mean the sheets below that.
no, these are mine.
Okay, just to make sure.
These are mine, not yours. You have to work on those. Right? So, let me make sure we understand that the continuous compounded thing. Right? So the whole idea was if you have a raw return like this, basically you take the natural log of it, and here I divide it by 100 because the original return were not divided by 100. So you do this, right? Log of 1 plus r, right? And this is the, right? Continuously compounded return that's equivalent to R, right?
In your formula is 1 plus or divide by
100, because the original returns, even though they mean 0.3%, they did not divide it by 100. They literally just left it at 0.3. So I had to make that adjustment. All right. By the way, you guys have noticed there's not much change, right, in terms of the values, right? You notice that? Right? If you compare this table with that table, the numbers are very, very close to one another, right? So, all right, so let's see those hands. Who has this on their laptop? You have to have it, right? Otherwise, we cannot proceed further. Okay. So let's do the following. So now we're gonna basically set up the environment that will allow us to compute the efficient right here. So that environment looks like this. Is it a lot of work? Yes, it is. But I trust you. You can do it. So let's do one thing at a time, right? So let's start with this, like a list of the stocks, just the names. So there's only 5 of them. If you could just type them in, right? And And the reason for that is you notice that we're gonna have to have the returns, right? Now, once you've typed the names, I want you to go back to your original sheet. And I want you to come up with two things. First, compute the averages, the expected returns for each one of the 5 stocks. How are you guys gonna do that? Just use the average function. So let's do that. And then raise your hand when you're done with it. Yeah. So we can wait some more though.
It's already on.
It's already on there.
Huh? Oh yeah, that's good. That's good. I was very generous. So average function. Okay. And then difference. Oh, I know why. Because we did it already. That's why. So there's no point in you doing this again. So difference from the mean, right? So difference from the mean. You guys remember this, right? Let's take one. Right? So difference from the mean for the first stock and then the second stock, etc. But putting it this way makes it easy, right? Because you have the mean right on top. So that's what makes it easy. What did we call this? What did we call this matrix again? There's a letter. What letter did you choose for this? D. This is the D matrix, right here. You notice that there's 5 columns instead of 2 now. Okay, so now that you have this, first thing you're gonna do is let's have a column called weight, and put equal weights on these stocks. So that's not what you see on the screen, right? But again, that's my word. You have to just start with equal weights, which would be
0.2.
20%. And so you have to type that in, 20%. By the way, that's what's known in the industry as naive diversification, because when you don't know much about investment, but you know you have to diversify, then the natural tendency is to try to invest the same amount of money in different things. Right? So it's not a negative thing, it's just called naive diversification because there's no work involved in it. Right? That's it. Are we done with the weights? Let me show those guys. So we're gonna work this one column at a time, as you can tell, right? You do need to sum these weights. So here's a cell that will include the sum of the weights. So you use the sum function, right? Once you're done with it, let me know. Let's wait some more. So put 20% for each one, 20% for each one of the stocks. Manually, yes. Later on, the machine will calculate it for us. But initially, the initial values would be manually input. We have to have this cell because the sum cell, because one of the constraints that we have to face, of course, is that the weights chosen by the machine, actually chosen by the algorithm, the weights should sum up to 1. Make sense? see those hands again. Okay. So, next column. You guys know what this is. What is that? It's the vector of returns. So did we have them in the previous sheet? Yeah, but they were a row, right? It's called averages, so you have to transpose that. So let's do that. So you've noticed we do this systematically, one column at a time, and not even the full column, just the top of the columns, because we have to take small steps, and then we can achieve great results. But the returns are already previously computed, so you just transpose them to put them here. Who's done with the column of returns? Okay. So now comes the big one. You know what the big one is, right? What was the formula for covariance, for the covariance matrix? Basically, you transpose the D matrix, right? Multiplied by itself, and then divided by the number of observations minus 1. So that's the formula I used here, right? The D matrix is I65 to M124, and you can see it here, right? And then I go back, but you can see it here, right? I65 to M124, right? That's the D matrix. So that's all I'm using here, literally. And then as usual, once you're done with that, let me know. And the reason why you have to go through all of these steps is because you will go through all of these steps with your own stock track portfolio. So you might as well practice, right? And no, you can't really use the same sheet because you're gonna have to add more columns, etc., etc. So once you guys are done with the covariance matrix, let me know again. So we're gonna wait a little bit. I need everyone in this room to raise their hand at some point when it comes to this covariance matrix. Because that's like, you could tell even just by the size of it, right? It's like the critical part of the whole operation. You don't know anything about the correlation or covariance structure of your portfolio, you can't really do much. Right?
Professor, what is that T2 arrows and then?
Oh, this was if in fact you downloaded prices like you will on StockTrack, then you have to transform that column of prices into a column of return.
R.
R is return, yeah.
Okay, I was also sure that's R.
Yeah, R is return. Any questions so far on basically row 1 through row 8. Is this clear to everyone? Yeah.
Professor, can you just tell me
Yeah?
the returns, one of the returns, how you did them?
Say that again, I didn't catch that.
For the returns, I didn't get them. Can you just
Oh, the
click on it so I
return.
can see it?
Okay, I got it. Okay, so the idea was the question, okay, there was a question, I might as well write it, let's say here, I can write it here. Basically the question, the idea was that if you do, this is not relevant, the picture, to what I'm saying, but basically the idea is that I downloaded returns directly from Morningstar Direct. That's one of the benefits of using it. But if you use StockTrack, which is much easier to use, then you download prices. So let's say price on day 1, price on day 2, price on day 3, etc., etc. And the whole idea was, okay, you have to convert this price column into a return column. And so, for example, return on day 2, it's going to be price on day 2 divided by price on day 1 minus 1. And then return on day 3 is going to be price on day 3 over price on day 2 minus 1. And, and basically there is no return for day 1 because there's only one price. So that's basically what I was writing on the board. Does that clear it up?
Yeah, thank you.
All right, no problem. Okay, so let's see. Okay, so let's see. Who's done with the covariance matrix? I know it's late in the day, but you can do it. Yeah, that's pretty good. That's pretty good. Right. So far, we have a list of the stocks in our portfolio. We have some weights, because we need some weights to define it as a portfolio. Then we have the vector of return, and then we have the covariance matrix, right? And then we have this cell that sum up the weights, right? Now, the whole idea, of course, is to have a particular target return and find the portfolio or the weights that minimize the risk, right? That was the idea, right? So first, or next, I should say, we have to have a cell that actually computes. We have to have a cell that computes the portfolio return. Correct? How do we compute portfolio return? You transpose the vector of weights and you multiply with the vector of return. That's what this formula does. So let's all do it, and let's do it physically, trust me. It might appear hard or tedious or something, but once you've done it, you're gonna be very confident when someone tells you something about portfolio return using matrices or using code or whatever. You know exactly what that means because you've computed it yourself. Then once you're done with portfolio return, just let me know. Okay, we're gonna wait some more. We need everyone to be on board, okay? For those of you who are done with this, what is the result you get?
$0.59.
0.59%. See, it's not as good as mine. All right. So let me see those hands again. Who's done with this formula for portfolio return? Let me investigate a little bit. So how you guys doing this? Yeah, let's see. The weights, no, just choose 20%, that's what I was saying. Okay. How are you doing? Good? Okay, so we're all on our way. Guess what's next? The next statistic we're gonna compute is portfolio variance, right? What is the formula for portfolio variance? The concept. Well, take the weight vector, transpose it, multiply by the covariance, and then multiply it by the weight vector again, right? That's it. No, but it's the shortest formula you will ever hear in your life, though. Just three things, right? Transpose weight times covariance times weight. That's it. Now, of course, entering it in Excel is a different story, right? You have to do this. You have to, right? So I'm transposing the weights C2, C6, and then I'm multiplying them by the covariance matrix G2, K6, and then I'm multiplying that result with the weight again C2, C6. That's what the formula is. So in theory, so normally this is the second time you guys are doing this, which is excellent. That's the only way you learn. And at some point you know the stuff by heart, like portfolio return, you transpose the weight multiplied by the return vector. Portfolio variance, you transpose the weight multiplied by the covariance and then multiplied by the weight again. Right? So this will take some time. Maybe I'm wrong. Who's done with this? Oh, a lot of people are done. Nathan, you okay? All right. So I'm going to ask you guys because you had some specific weights, right? You remember that? Like equal weights? What is your variance? 0.08?
Yes, 0.0%.
So are you saying you chose a portfolio with lower return and higher value. Congratulations. That's great. All right. So now, this part is very easy. Everyone should raise their hand almost instantly. Because how do you go from variance to standard deviation? Anyone? Square root, right? That's it. Square root, right here. Just the square root. Questions about everything we've done so far? All we've done was prepare the environment, right? So that we can go ahead and calculate the efficient frontier. The definition of efficient frontier is what? It's the set of portfolios that, for a given return, has the smallest possible level of risk. That's it, right? That was it. We also know a couple more details. That efficient frontier should start with the MVP, meaning the safest possible portfolio. You remember that, right? And then it should end with this return of the highest return of a single stock, like 1.19%. Right? Question. All right. So we are ready to do some stuff. So first of all, the result that we're looking for is this result, right? So I start with the MVP and that gives me a particular return. And now we know we should never target a return lower than that. And I end with the highest return of any individual stocks, which is, again, Johnson & Johnson, 1.19%. And you guys see the solution here, 100% invested in Johnson & Johnson. Okay? So how are we gonna do this? Well, we're gonna use, so there's many solutions, but on Excel, the best solution is to use, so if I go into my data tab, yeah, I always forget to do that. Terrible. So, got it. I'm gonna go to my data tab and normally I should see analysis and all that, and I don't, right? There's nothing here, right? And so what I'm gonna do is I'm gonna look for a tool called Solver. Raise your hand if you've ever used Solver on Excel. And it's fine if you never used it before. So Solver does a lot of things. Well, obviously it solves problems. But one of the things it does is what's known as quadratic programming. What is that? Well, if you have some equation where the unknown are squared, so you have a quadratic equation like x squared and y squared, and you want to minimize or maximize that equation, that's quadratic optimization, right? But it's programming because we want to maximize or minimize, so in this case, right, we want to minimize variance, right? And we remember, I don't know if I erased it, variance have squared weights, right, in the expression. And the whole idea is to find the weights that minimize variance, the squared expression, right? But subjected to a few constraints, right? So that's why you don't just compute it using derivatives and all that. You have to use algorithms, right? So there's many algorithms that solve this problem, and it's an old problem. And the most famous algorithm is known as the simplex algorithm. I'm not going to go into that. It's already in Excel, so why bother, right? So I'm looking for solver. And normally, when you click on data, then you're going to find solver somewhere. It's not here. So what we need to do, so first of all, does anyone have it on their ribbon, the data ribbon, or not? You have it already, okay.
Yeah, because I activated from the admin.
Great. But basically the idea is if you don't have it, you want to go on File, right? So I clicked on File, then scroll down to Options, right? And now you have this pop-up menu, right? And the title of the menu is Excel Options, right? So what you need to do is scroll down the menu, the left panel, until you see what? Add-ins. Add-ins. Click on Add-ins. And now, at the bottom you see Manage Excel Add-ins, right? So let's click on Go. And what do you guys see? Another pop-up menu. What should we do here? Click on Solver Add-in. That's it. So if we do that, let's do that. Click OK. Did you guys see the miracle that just happened? Well, it's not a miracle, it's a software. But basically at the extreme right of my top screen, on my screen top, I all of a sudden have Solver that's available there, right? So Solver is just a form that allows you to express the problem you're trying to solve, right? Questions so far? So raise your hand if you now have Solver on in your Excel workbook. If you don't, you cannot move forward. All right. Although as a student, we did solve these problems manually, but I don't think you should go through that. Let me see those hands again. Okay, it's enough for me. It's very late and a lot of people are just. So, fine. Okay. So what are we gonna do? We're gonna formulate the problem, and it's gonna look like this. So let me show you what it looks like. And so I click on Solver. Do we all see this? All right. Let's read it together, because obviously I already have some stuff here, and I'd like you to understand what the stuff is, because we're going to be inspired by it, right? So what does it say? So the first thing you tell Solver is your objective. What are you doing? You're maximizing something, minimizing something, or you're targeting a particular value. So what we want is we want to minimize variance, right? The variance of a portfolio. So set objective, you guys have noticed, I chose C13. What is C13? It's the cell that contains portfolio variance. The formula for portfolio variance is in there. Do we all see this? So that's the first thing you tell Solver. I want to minimize portfolio variance. Questions about that? Right? what are your variables? In other words, which cells does the software, the algorithm change to come up with the solution, right? What is the unknown? What are the unknown variables, right? And again, it's an algorithm. It does make educated guesses, right? But it's not gonna compute. It's not computing some sort of mathematical equation. So what are we looking for? We want to change C2, C6. These are unknown, right? We want the algorithm to consider these as the variables. C2, C6. So I chose C2, C6, right? And then subject to constraints. Let's read it together, right? So first constraint is C12 equals A20. What in the world is that? So what is C12? Portfolio return. I want a particular value for the portfolio return. And that value is in A20, right here, 0.82%. You guys see that? So that's the first constraint that I have expressed, correct? So don't do anything for now, just let's try and understand what's going on. And then we will manipulate this together. What is the second constraint? Anyone? What does it say? Yep. Mara.
The weights have to be greater than 0.
Yeah, all of the weights should be greater than or equal to 0. Right? So C2, C6 greater than or equal to 0. Right? So in this setting, and this is true most of the time anyway, we do not want to have short positions here. Right? Because when we do this, it's for the very long term. And there is no such thing as a long-term short position. Right? So, and then what is the last constraint? Yeah, the sum of the weights should be 1. This is why we had C8. We had a cell that computed the sum of the weights. Right? So that's the general way we're gonna come up with all of these portfolios, right? Questions about the idea behind the solver setup? Yeah? Huh?
On the solver.
Yeah?
Can you please repeat on the solver?
So solver, so you have to start with the objective, right? So the objective is to minimize variance, right? Minimize risk. So literally the objective cell is C13, which is the variance cell, right? And then you choose min for minimization, right? And then the next choice is what variable cells should be changed. In other words, what are the unknown variables in this problem? Well, it's the portfolio weights. We're looking for the portfolio weights. Where are they? They are from C2 to C6. Right? So that's the problem, right? We want to minimize the variance cell by changing the weights, right? But what's complicating matters is there are some specific constraints. Number one, we want a particular return. So in this case, I chose the return that's written here in A20, right? So that's the first constraint. C12, which is the portfolio return cell, should equal A20, which is the cell that contains my target return. Then the second constraint is what? All of the weights should be greater than or equal to 0. So C2, C6 should be greater than or equal to 0. And then the last constraint is that the sum of the weights, which is computed in C8. C8 has that formula for the sum of the weights. So you want the sum of the weight to equal 1. Alright. And so what I wanted you guys to do for now is just understand what this expresses. Any questions about this? Any additional
Why
questions?
you said objective is minimum variant instead of maximum return?
Because when we discussed the idea, right, that was how we did it, right? We chose target return, and we chose the one on the efficient frontier, which has the smallest risk, right? And there's nothing wrong with doing it that way, as long as we start with the MVP, right? So that was the idea, right? Also, that's the traditional, just the traditional approaches. Yeah.
Why you put the A20 is like higher than MVP?
Yeah, just the client wanted more return. Nothing wrong with it, right?
Yeah, so but why is A20 not like A21?
Oh, totally random. It's just for illustration at this point. Yeah, good question. No, it's just for illustration, right? Right.
So,
Yeah.
to the previous question, you practically said risk, which is typically the financial advisor approach, right? They ask a client, okay, what's your risk appetite? And practically they start from there, right? That's usually the
So, yeah. So Peter is talking about the fact that in practice, a lot of advisors are trying to find a way to get you to say something about how much risk you're willing to take, right? That's always been problematic.
Well, I'm saying because you also practically define the risk.
That's the thing, you know, here it's very narrowly defined, so there's no misconception about it. But in practice, you know, when you talk to clients, you don't necessarily want to explain standard deviation and that sort of stuff, right? Okay, so let's get going. So the first thing we're gonna do is actually try and find, guess what? MVP. Right? Again, I know it's late, but how would you guys change what you see on the screen on Solver to get the MVP? Do you still want to minimize variance? Yes, yes, we do. Because the MVP is the safest portfolio of all. So we still want to minimize. Do we still want to find the weights that minimize the variance? Yes. Right? But do you want the return to be 0.82%? In fact, do you want any sort of return at all? Do you have any target return when you look for the MVP?
Just minimum.
Huh?
Oh, wait. I can't think at this point.
Yeah, that's my point. Oh, most of us can, but
Well,
anyway.
Gross is bringing us in at like 10 o'clock in the morning.
So, anyway. So we want the safest portfolio, period, regardless of return. Is that clear to everyone? So that's how we're gonna find the MVP. So, here's what you're gonna do. First, make sure you have Solver in front of you. Make sure, let's do this together. Make sure you choose C13 here, which is the the variance cell, right? Right? As soon as you're done with it, it's just one thing, raise your hand, we move on, right? Then the next thing is click on min. I'm not gonna ask to raise your hand, but I'm gonna ask you to raise your hand when you choose C2, C6 in this area of changing variable cells, right? All right. So now, how do we add constraints? So the way you add constraints, okay, first of all, before adding constraints, okay, Malcolm, you have a question? Or you were saying you're done? Okay, so before adding constraints, let me deal with a particular problem here for me, because you will have to deal with it later as well, which is I do not want this particular constraint, right? We want the safest possible portfolio, period, regardless of return. So I click on it, and then guess what I'm gonna click? Delete. There you go. Now, you will have to add these two constraints. How do we do that? Well, here it is. You know what to click. Add. Right? Add. And then what was the thing that you needed to add? You needed to add that the sum should equal 1. So here you select C8, right? And then, right, you select C8, and then here in the middle you select equal, right? And what you write down here on the constraint 1, just write 1. And then you click OK. That's gonna be added, right? I need to see you do it. I don't see anyone moving at this point. Let's do it. Right? Yeah, you done? Yeah? You guys are done?
Yeah.
Okay. I'm gonna blindly trust you.
The one, yeah, you can go back and
Yeah? Sure.
the order of this constraint is.
No. So that's a great question. Does the order of the constraints matter? The answer is no. Right? So I want you guys to add the next constraint, which is you want the weights to be greater than or equal to 0. You know what to do. Let's do it. And so at the end of the day, you should have what I have on the screen. Who has this on the screen? Okay, so if you did it all right, then we should all get the same result. Let's try. What do we click? Solve. Okay, you click on solve, and then solver says, do you want to keep the solution? And we say, of course. So you click OK.
Or sometimes it says solver did not converge to a solution.
Yes. So, do you guys notice something? Look at my weights, right? They've changed, right? And yours too, right? You don't have that 20% magic anymore, right? Now you have the safest possible portfolio. Oh, by the way, I already worked on this, and I already listed it on a row, right? But you notice that this thing on the row is what I have there, right? With some slight differences, right? As algorithms will go, right? But that's basically the idea, right? So these are the weights that you see here. Questions about that? So we know that is the starting point of our efficient frontier. We should never target returns that's lower than, here's the return, 0.77%. Questions about that? And so the smallest possible standard deviation is 2.77%. 71%. Right?
Is it typically enough to run the solver once?
Yeah. Yeah.
Just
Because if it's not gonna work, it's not gonna work.
Just because you said there is a slight difference between the runs.
Yeah, yeah, well, so the difference has to do with the initial values they started with, right? Because the algorithm is basically approximating the solution, yeah. It doesn't make sense though to rerun it. I know what you mean, but it's sort of like you have a sampling distribution and then maybe you take the average or something. Not worth it, right? Questions on how to get the MVP?
Professor,
Yeah,
can you please repeat this constraint?
yeah,
Yes.
yeah. So, let's see. Here you go, right? So there's only two constraints here. I'm not targeting any returns. So you see the first constraint, C2, C6, greater than or equal to 0, right? How do you do it? You just say add, right? And then you select C2, C6, like here, right? The weight. And then the middle is greater than or equal, right? And then the constraint window, you just type in 0. That's it. Make sense? Yeah.
Solver, maybe selected to save the
Yeah,
this.
yeah.
So it can typically it has only one state what it saves, right? It is not like if I pick a different cell, then it recognizes, oh, I want to optimize that cell. That comes up to the difference. So there is always one. So
Yeah, right. Questions? Question? Yeah. Square root.
Yeah. So where I did
Okay, okay. Yeah. So you do have to use that formula you're using now, which is equals C13 to the power of 1. Absolutely. Right. So any questions on the setup for solver or the concept of MVP? Now, here's the next step. We know this is the smallest return we should be targeting. Again, remember something I mentioned earlier. We're not going to do it here. But when you actually compute the expected return for your portfolio, it might be that your expected return is below that. In that case, you have to change the solver settings. Instead of minimizing variance, you maximize return for a given variance, right? We will talk about that when the time comes. But for now, we do the routine, normal situation. So we know this is the smallest return, 0.77%. We know the highest return is 1.19. And so what I did was just pick, I needed, I don't know how many this is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 returns. We know it starts at 0.77, ends at 1.19. So basically you have to compute target returns, that have equal increments, right? So that you move from this to the smallest return to the highest return in a smooth fashion. Questions about that? Right, so you can do it in many ways, like you can compute the difference and divide it by 10, and then you add it to the new value all the time or something. Here, I just added 0.05 and it just worked out, right? Questions about that? So that's the next step. Come up with a list of target returns, like at least 10 of them. We already have 2, the smallest and the largest. Find 8 more, right? That's equally spaced, not a complicated story. Questions about that?
How did we know the highest one? Because Johnson & Johnson.
Yeah, that's it. In a portfolio where you can only have long positions, the maximum return you can ever get is the same as the return of the highest, the return of the stock with the highest return. There's no other way. If we, for example, allowed short positions, then we could borrow money to buy more stocks. Then it's a different story. Yeah.
Make a difference, like going up by 1, 2, 5%, like doesn't make a difference at all?
The best, it makes a difference on your picture. So you want a good looking picture, right? And so what you want to do is just make sure you compute some equal increments, right? Right. Other questions? So now, so you guys can tell me actually, because I don't even remember how I got this 0.05%, but somehow it works out fine. Well, it's not equal, right? If you wanted an equal increment, how would you guys do it?
By changing the weights, I'm assuming? Or-
No, here.
No?
No, I'm talking about
Oh.
here. How do you fill out this column? Because here I just randomly added 0.05 and somehow it worked out. But if you wanted to do it scientifically, how would you do it? No, yeah, I know, but my point is not so much it's just the numbers. In other words, what formula should we put here instead of A19 plus 0.05%? So one way is just compute the difference, right, between 1.19 and 0.77, and then divide it by what? 1, 2, 8, right? Divided by 8, right? So you can do it like that. So why don't you do that? And if you don't want to do it, then do it my way, which is just type in all these numbers. Either way, but you have to find a way to do it. You need that. You need this column to be filled.
Yeah, but this can be equal, how about like we divide it by 10, something like this, so really small,
Well, make it so that when you add the last one, it's exactly 1.19%. So I think divided by 8 will work, right? Right. Raise your hand if you have equal things here. Okay. Well, it's 9:30. So we're gonna stop it here. But if you're adventurous, you should do 2 things. Look, you already know, because you have it on Solver, right? You have the setup for MVP, right? What's missing for you to get the other portfolios? What's missing on this Solver setup?
Get straight.
One constraint, which is what? The portfolio return, which is C12, equal one of these numbers. You add it and run Solver, right? So if you're adventurous, I mean, we can do it here in class, but if you're adventurous, you can do it on your own before class. And push this further. If you're even more adventurous, you can anticipate the next assignment and do this on your portfolio. I know it's a lot of work. Someone has to do it, though. That's where you get paid the big bucks. Right? So, questions? Right? And so if you follow carefully, you now will have at least 10 possible portfolios based on the choices that you've made on stock track, right? And we're gonna discuss further, right? But this is very important. Is this clear to everyone? All right, it's time to get that here. Add that constraint that says, portfolio return should